Hello and welcome back to Let's Code Physics. We are in episode 4 of our series simulating the motion of various objects in space interacting via gravity. We took a look at a couple of different situations last time. We looked at the Earth going around the Sun again, tried adding in a second Earth because of the immense mass of the Sun. It didn't make a huge difference, so that's kind of nice to know that we can't be thrown off orbit that easily. I did go back afterwards and try out a different scenario with adding a second sun and had some better success with that. So we'll get to that in a little bit on today's video. The main objective for today is to begin incorporating some more advanced plotting techniques into these codes. We're going to be using what's called a phase space plot. We're going to make a phase space plot for our Earth and Sun system, our Earth and 2-star system, and the 3-star system that we were working with last time. Speaking of that trinary star system from last time, I did take a look at the situations where they were, rotating around each other and then suddenly flying off. Turns out that is an error in the code. The way I figured that out was by putting in a calculation of the total energy. Now this calculation of the total energy is at the very beginning of the code, so it calculates the total kinetic energy, then calculates total potential energy, and it stores that information as energy underscore 0. So that's the energy at the very beginning at time t equals 0. And then I've got the same calculation in later in each step of the loop. So for each step forward in time that the code takes, it again evaluates total energy. Now the total energy should be conserved. The conservation of energy is one of the great principles of physics. And so if there's a non-conservation of energy, then it indicates that there's an error in the code. And basically what this does is it calculates the energy at that particular time and then compares it to the energy at the original time. So it's saying if the change in the energies compared with their average is greater than some tolerance, I think I made it like 10% or something like that, then the code is going to stop. That's what the going variable does, is it tells it whether to go. So instead of the loop being while true, it's now while going. So if we are going, then it goes. If we're not going anymore, it doesn't go. Makes sense to me. And it's also going to print out that there was an energy error and tell us what the current energy is. So we'll have a printout of the original energy and then the energy that triggered the error. So this is the same setup that we had last time, the same masses and distances and initial velocities and everything that we had last time. Oh, no, wait. No, it is not. I found a system that was stable for longer. So this is something better than we had last time. So this one I gave them a little bit of momentum to the left. They've also got slightly different masses. I forgot I was saving this for later. But anyway, what we'll see is that when these things do fly off from each other, it's due to or it coincides with the energy suddenly jumping. So this is one of the limitations of the Euler-Kromer method that we've been using for nearly every episode so far. We've been using the Euler-Kromer method. In season 2, starting in the spring, here you see they've flown off from each other. Except it hasn't triggered the energy error yet. Yeah, so our total energy is negative at the beginning. So let's see what happens. Let's let these run for a little bit. In season 2, we'll start working with some more nuanced computational machinery, some stuff that helps avoid errors like this one where there's an issue with the energy. And yeah, I'm starting to think that red one is not coming back. When you see them start to take on the straight line behavior, chances are they're not coming back. But this does give us a few cycles to work with later on when we start to work with phase space plots. So that's sort of the main star for today, is the phase space plot. So usually when you graph something, so when you were in middle school and first learning to make a graph, you graphed your dependent variable versus your independent variable. And I need to remember that this image is flipped. So you graphed your dependent variable versus your independent variable, right? So if you were me and you were doing your 7th grade science project, this was the amount of deterioration in some food object that you had placed in the dirt versus the number of days in the dirt. And I had to figure out how to measure amount of deterioration. So I said, I'll weigh them. I'll take the weight of them at the end of each day. And it turns out that soil is moist. And so that means that some things like socks, like I tried, will tend to absorb moisture, and that will make the weight increase instead of decrease. So it didn't actually look like they were deteriorating. But the idea is, usually when you graph something, it's usually dependent variable versus independent variable. And the great independent variable of the universe, of course, is time, right? Time is going to continue on regardless of what we're doing with our experiment. So 9 times out of 10 in physics, we're graphing something versus time. So if I wanted to, for this, say for the Earth versus the Sun, I could graph the Earth's distance from the Sun versus time, and it would come out, looking, like a little bit of a wavy graph. And that's interesting, but it doesn't really give me an idea of how the actual properties of the system are related, because while time is the great independent variable, it's also kind of arbitrary. Right, so I choose as a physicist when to start my stopwatch. I choose how long to record it for. I choose, how many intervals to record it. What's really of more interest is how the dependent variables relate to each other. This is more of interest both in terms of the information about the system, and aesthetically, they make prettier graphs. And as I often say to my students, all I want out of life is some pretty graphs. So what I've done is I've gone ahead and started up a phase space plot in the Earth and Sun simulator. I went ahead and did it just so that way, I could show it to you and then construct it in the other simulations. So what I've done here is I've created a couple new scenes and a couple new graphs. The first one is going to be for the velocity of the Earth versus r of the Earth, the distance the Earth is from the origin of our coordinate system. And then the second one is going to be the angle that the Earth makes. So when the Earth starts out this way, no, I can't go that way. Yeah, when the Earth starts out this way, it's going to rotate around. And so you can measure its position in terms of its distance from the origin and in terms of the angle that it makes. So that's your pretty typical polar coordinates. And I've gone ahead and made some minimum and maximum values here to just so that way they show up nicely. Now, one thing you'll notice is that you still have to pick one thing versus another thing. So for example, for the first graph, we're going to be looking at the Earth's speed versus the magnitude of its position. Now that's leaving theta out of the picture. So really, these are all three varying with time. And in fact, really, I could have a theta for the Earth's position and a theta for the Earth's velocity. So really, it's a 4-parameter system, or 4-dependent variable system. The magnitude of the position vector, the angle of the position vector, the magnitude of the velocity vector, and the angle of the velocity vector. So whenever you're creating a phase space plot, you're having to make a choice. You're having to say, I'm going to only look at these 2 variables. The rest are also going to be varying, but you can kind of think of it as they're varying in other dimensions that we aren't graphing, right? So this is really a 4-dimensional output, but due to budgetary constraints, we're presenting it as a 2-dimensional graph. That's an adaptation of a joke by Stephen Hawking. I'll post a link to that joke because it's funny. So up here at the beginning of the code is where the graphs are created. So there will be one for velocity of Earth versus distance of the Earth. One will be for the angle of the Earth versus the distance of the Earth. I've got this in the right order. And so then all we have to do is within each loop of the code, we just have to do a calculation of the position of the Earth, the magnitude of the velocity of the Earth, the angle of the Earth, and then we just add each pair to the graph. So you can imagine you can make a phase space plot for every pair of variables that you care to create. We're just going to stick with 2 just for demonstration purposes here. So we're going to run the code, and these graphs are going to update at the same time that the animation runs. So you can see here we've got the angle versus the position of the Earth. So the angle, of course, is changing. It's changing at a different rate just because it's going around differently. Here we've got the speed of the Earth versus the distance of the Earth from the center. Now, there's a little bit of an artificial jump here. So this is an angle. So angles, reset every 2 pi radians or 360 degrees. So this graph is only going from 0 to pi over 2 and then from negative pi over 2 to back to 0. So that way it covers an entire range. So it's going to go from 0 to pi. It's resetting. 0 to 180. Yeah. Then it's also going to come back around here. And basically, by the time this makes a complete cycle, this thing will have made a complete cycle around and will continue on. Now, this thing is a little bit less interesting. This is the velocity of the Earth versus the position of the Earth. And so all it's doing is tracing back and forth along this line. Since the Earth makes this nice closed loop that repeats pretty regularly, the data along this phase space plot just go back and forth and back and forth. Now that's interesting because it indicates that we have a regular periodic orbit. You know, it doesn't jump up here or down here or zip off this way. And over here our football shape is almost complete. So basically, once this thing reaches back up here to the original point, the Earth will be back up to the point here. So that kind of illustrates to you that a phase space plot is showing the same information, it's showing the same motion. All it's doing is showing it differently, right? So this shows you what it looks like in real space and time. This shows you how our speed varies with our position. So the closer we are, the faster we go, right? That's conservation of angular momentum. And then this just shows how our angle varies with our distance away from the Earth. So as the thing goes around, our position goes in and out a little bit. So that's pretty cool. What I'd like to take a look at next is I mentioned that I had made a code where I added an additional sun. So we tried adding an additional Earth last time. Not a whole lot happened. Here's what happens when you add an additional sun. So in this case, we're going to have our normal yellow sun, our normal Earth, and there's going to be an extra red sun in there just for kicks and giggles. And so here we've got the Earth going around. The suns, of course, are attracted to each other. So our sun usually doesn't move like this. And here they come by. There's this conservation of angular momentum here. They can't get too close. The Earth is making its pretty normal orbit at this point. Let's zoom in a little bit here. But here you can start to see our orbit gets a little bit distorted. You see it's not coming back down flat like it was over here. These two, of course, are going around in curves like we saw with a binary star system before. So the Earth isn't really affecting these two, but the presence of the second sun is definitely affecting the Earth's orbit, right? It is curving up way too soon. And it is at right about this point that I'm pretty sure we're all fried. Happy holidays, everybody. And then, of course, by the time we get out to here, we are now farther out than when we started. So right about here, we got fried. Right about here, we are getting frozen. It's not over yet because this is still a nice bound system. The Earth is coming back around. This is where it gets really interesting. I watched this a couple times over to make sure I understood what was going to happen and everything. Again, the two stars are they're not very perturbed by the Earth, right? Because our mass is very, very small compared to these two. The red one I think is about half the mass of the sun. So here we are almost. We're going right in between the two suns. And here's some good news. We do actually end up with another elliptical orbit here. We catch up to the sun with an elliptical orbit, so that's nice. Yeah, we're definitely fried at this point because you imagine this is about a third of our usual distance to the sun. And of course, if we didn't get fried before, here we are definitely getting fried as that second sun comes in to grab us. Oh yeah, we're definitely fried there. Oh yeah. Oh, here we go. We're getting into a stable orbit, at least. We're passing closer than Mercury, I believe, at this point. So our oceans have definitely boiled away at this point. But at least, we're in a nice, somewhat stable orbit. That's good to know. Oh, here comes the red sun again. Oh, we just can't stay away from these things. And there's another little almost stable orbit there. Okay, so, we're I should have looked up what the distance of Mercury is. I suspect this is closer than Mercury. Now, of course, these two are going to keep going back and forth, closer and farther and closer and farther. Just like we saw with the binary star system last time. Oh, and there we go. And at this point, we have gained enough speed. We are swiftly going away. We are definitely frozen over at this point. I don't think it's coming back at this point. So that was really interesting. Feel free to rewind as many times as you like. What we're going to do now is we're going to add in the phase space plots that we had before. So up at the top, we're going to add in our phase space plots. So first, let's just create the graphs. Let's see here. I want to go back to this one. Yep. So here's where I'm graphing things, or here's where I'm creating the graphs for things. Cool. So let's see. Let's keep our original stuff at first. V of Earth and R of Earth, theta of Earth and R of Earth, and then we'll take a look at maybe the two suns in a little bit. And then I need to go down here, and then I can just do the same thing here at the end of the loop. I'm just going to grab these and copy and paste them in here. Here's where we graph things. Okay, the Earth is still bouncy ball number 2, I believe. Yeah, Earth is still IBB2. So we're just going to have the same graphs that we had before. So we're going to see that same animation again, only now we're going to get to see our phase space plot. So we expect these to look pretty similar to what we had before, because originally the Earth was not terribly perturbed. And it occurs to me now that I need to resize this thing. There we go. Okay. Only now you see we've been deflected. So here we couldn't, so this is the advantage of the phase space plot, is here we couldn't really tell that our orbit had been affected yet, but here we can definitely see that it's been affected, precisely because this thing was originally, a line that did not change, and now the thing is curved away, and I don't think this thing is going to auto scale for me. So there we go. Our angle has definitely taken a different approach, right? So instead of being this nice football shape, it's now shooting off this way. I did not anticipate that I would have to zoom out on this thing. I might end up redoing this with the... but here we're coming back. So yeah, so we are definitely not on that straight line trajectory anymore. So this tells you that there is something weird going on. This tells you something weird going on. This also gives you an idea of how much faster we're traveling, right? That the R is changing so much and the theta is changing so little. Oh dear, here we are just speeding up a lot here. Oh dear, look what happened to our speed. Oh, that is a tight turn right there. Let's take a look at our angle. Oh my. When I post this code online, I will get rid of the locked scaling so that it automatically scales the graphs and everything. So you get an idea that phase space really does give you a neat idea of how the system is behaving. So this tells me, that this thing took some really rather strange turns, quite literally. This one, of course, is interesting because the angle has to, reset every pi radians. Cool. So that gives you an idea of what phase space plots do for you. Let's take a look at it now with our trinary star system. And I'm actually going to... should I start these? I will copy and paste, but I'm going to adjust those this time. Let's see, copy, and yeah, there is our energy tolerance. Yeah, 10%. So here we're going to create graphs for things. Only this time I'm going to get rid of this xmin and xmax, ymin and ymax stuff. There we go. Save. This is trinary star. Yep. Okay, so now we don't have the Earth anymore. So let's look at star number 1 is the more massive one. So let's look at its position versus the position of R2, and then let's look at R2 versus R3. So R2 and R3, or star 2 and star 3, are the same mass and starting out, in roughly symmetric positions. So that'll be interesting to see the difference between the unequal masses and the two of the equal masses. And then, of course, I want to make sure that my axes are labeled. There we go. Paste. Paste. Okay, so I've gotten rid of the min and max stuff. I've just commented that out. And now what I need to do at the end is I need to add in the graphs of things. So let's see, what did I call these things? I called them PS underscore graph. So PS underscore graph 1 dot plot and PS underscore graph 2 dot plot. And so the first one is supposed to be, oops, I got these backwards, R2 versus R1 and R3 versus R2, just to get our naming right. So this needs to be R1 and R2, so this needs to be magnitude of IBB, of BB list dot pause. Oh, this needs to be of item 1 because I'm doing R2 versus R1. The other nice thing about phase space is it doesn't necessarily matter which one you put on which axis because it's just going to turn it, you know. So let's see. So that is R2 versus R1, right? So R1 comes first and comma magnitude of BB list of 2 dot pause. Cool. And then for the second one, we're doing the same thing except it's going to be 2 and 3. So let's copy this here, paste. So what I'm doing is I'm just accessing the position of each of these and then taking their magnitude. Okay, cool. I haven't done anything else to change the code. It's still the same animation that you saw earlier. So we're going to see the same little spiraling animation up here. And I have, oh, that's right. This is why I like to copy and paste, because I have to tell it that this is the position of the thing that you're graphing. It's not just the ordered pair. You have to tell it that it's the position because it might have other arguments. There we go. Okay, so here we've got our R2 versus R1. So this is the position of the red one versus the position of the yellow one, and then this is the red one versus the blue one. So what you notice is they're obviously behaving differently because this yellow one is different than the other two because it's got more mass than the other two. It's got this sort of general repeating structure, just like these are repeating each other, or the motion is repeating, it's just moving to the left each time. But you notice this one, they're sort of, you know, this kind of motion indicates that they're circling each other, right? So the red and the blue one, they're just sort of following each other, while the yellow one has this much different approach to it. And of course, this thing is cyclic, so it's just going to keep going this way. These are going to keep going, you know, up and to the right. They're never going to, you know, sort of double back on themselves. But this just gives you an idea of some of the interesting stuff you can observe. Let's take a look instead of at the... let's take a look at how their velocities are behaving. So what I could do here could be, I could say that I want to have V1 versus R1. So V1 versus, excuse me, wrong thing. V1 versus R1. So I could look at their velocities, and then I could do V2 versus R2. And then all I have to do is change the thing inside here. So all I have to do is make this velocity list of 1 and make this one velocity list of 2. So here I'm not plotting position versus position, I'm plotting velocity versus position, but for each individual star in the system. So let's take a look here. Oh, right, the velocity doesn't have a position, it's just a vector. It's like the third time I've made that mistake. Okay, cool. So these show you the velocities. So again, this is the yellow one. This is the red one. So they're behaving somewhat similarly, right? So they've got kind of the same motion, but they are behaving notably differently, again, because the yellow one has a different mass. So this gives you an idea of just how different... Oh, I don't want to cover that up. What if I... Oops. Did not mean to take away everybody else. Y'all come back. I said come back. Oh, I clicked on the thing. Okay, there we go. So this gives you an idea of, you know, just how one variable is changing with another. So again, this one, you know, you've got one regularly repeating pattern. Here you've got a different regularly repeating pattern. And again, the idea is that they are repeating. And so even though they're moving to the left, this on the animation, this shows you how the variables themselves are repeating. Where things get really interesting is where you get what's called chaotic motion. Chaotic motion is where something will go back in on itself and sort of fill in the space. And of course, this is where the energy error occurred. So this is where we've got the red one shooting off. And so things look a little bit different now. Again, this is an indication that we had an error, because here things are nice and consistent. Here things start to break apart a little bit. Let me get my code back up here. And so we can play around with this some. We can change the masses. So like, for example, we can change the initial velocity of the yellow star, the heavier one. Let's see what we get when we make this thing. I gave myself a note to try out -0.5, and so we're going to cut its velocity in half. And so we're just going to compare the phase space plots that we get. So we get a very different animation here. Wildly different animation, right? And of course, we get wildly different phase space plots. Now, this is not quite so nice and repeating, right? So this is not so, this is not them, cycling around each other like they did before. Here we've got things are much messier, right? But you could trace each one of these along to figure out what they were doing. And of course, here we've got the thing shooting off again. I can also try cutting that in half. So let's see what happens when we give this thing even less velocity. Okay, so here we've got a little bit of a repetition going on. So there's some periodic behavior, but then this thing has gone off, but it hasn't scattered off yet. The blue one is coming back. These two are actually coming back around. This is actually one of my favorite animations that I got the other day. So the phase space plots are just doing wild things at this point. And I think we probably end up with something shooting off again. So now it's the yellow one coming around. And my code seems to have frozen. Oh, I probably got my energy error. Yep. So here you saw the energy error happen. Our initial total energy was -1.25. So negative means its bound state. Here the total energy came out to a +64. So it's now a scattering state. So yeah, that's a problem with the Euler-Kromer method. Let's try one more thing, and then we will talk about what we're going to do on the next episode, because I'm really looking forward to the next episode. We're going to try 0. We're going to try putting the yellow star initially at rest. And of course, that means things are going to be, again, wildly different. So our phase space plots are just doing all sorts of incredible things. I would love to just make, a whole bunch of these and then print them as a coloring book, because I think this would be fun, for like, to color in or something. Oh, and there our energy ran away. You can also see that our energy ran out of control by the steep shape here. So phase space plots tell you a lot. While we get, a lot of pretty things off of here, the phase space plots do help tell the story. So I hope you've enjoyed taking a look at the phase space plots. There's another extension of the phase space plot. Like I mentioned, this is only showing you 2 of the possible independent variables. I mean, you can even get 2 windows going at once. It still doesn't tell the whole story. Another way we tell the whole story is with something called a Poincaré plot. And what that does is it takes a phase space plot and it allows you to work with a multi-dimensional phase space plot. It just reduces it down to a screen that you can see. And that's what we're going to be working on next time. So thanks so much for watching. See you next time. Bye-bye.